By the way, if anybody is interested in giving a talk, you just heard an excellent one by Caleb, and he and I are going to, we did a podcast this morning. Link comes out a little late, but we'll be putting that on the Facebook page for the Memphis Astronomical Society. But if anybody's interested in giving a talk, let me know. I am the Vice President of Programs for the Memphis Astronomical Society, so just let me know.
And finally, NASA announced today that there are 1,284 new planets that were discovered by the Kepler Space Telescope.
Okay, first of all, NASA, stop this. I can't. You're just overloading us. First of all, it's okay if you're going to give us a new planet, like every few years, be like, whoa, got a new planet. Last week, they said there's 3 new planets. They have the same kind of stability that we do. They could be us. And now you're like, whoa, we just found 1,300 new planets.
Yeah, 9 of them are habitable, which is crazy. But this is the first NASA mission that could find potentially habitable Earth-type planets.
Is it called habitable? Is that
habitable? Remember yesterday I invented a word. Today I am giving you.
I thought it was habitable.
Is it? Am I just? Really?
I think it is habitable.
Am I saying it wrong?
Yes. Yesterday I didn't know a bison was a mammal. It's okay.
Well, who uses that word? But I think this is great. I'm so on board because one of my biggest fears in life is we're supposed to blow up, right? Like the sun is going to blow us up.
No.
Yes, we are.
Christine, we're not going to get blown up.
No, we are. As the Earth gets closer to the sun, we're going to blow up eventually.
Christine, you're 29.
No, it's true.
This is going to happen in 40 light years.
I know. I'm just saying, like, my family tree, like when my kids have kids, I don't want to think about them blowing up. I would like to know that eventually they have a great home to have. I would like for the space people to find some place where my kids, I want to know that they will have a place to live. They won't be blown up.
God, between me not understanding a bison was a mammal and you calling them space people, we've hit a new cerebral low on the show.
I've had so much coffee. Okay, that's the news.
Space people, get your act together. You're freaking out, Christine.
No, I just don't want to blow up. That's it. That's the news.
Christine, the news.
All right. So a little insight into the mindset of millennials. So, sorry. I thought it was appropriate to say, given the current audience, but we are living in unprecedented times of discovery. Growing up, most of us, there were 9 planets in the universe. And, of course, that's been downgraded recently to 8 in our solar system. But it's now believed that there are as many planets in the solar system or in the universe as there are grains of sand on all of the beaches and deserts of the Earth. So we've gone through, in the last several hundred years, there have been several revolutions in thought that have brought us to this point where the technology is there, the ideas are there, the scientific method is there, and as a result, discoveries are also there. So the Kepler mission is one of those discoveries, one of those instruments that has been used to really propel our knowledge forward. So just kind of a higher level look. It was launched in 2009, and its sole purpose was to find exosolar planets. You know, planets outside of our solar system where the space people can eventually live when the Earth blows up in 40 light years. So, and this is kind of how it works. You know, there's 200 billion stars in the Milky Way galaxy. It stares continuously at one section of the sky, and you get a large field of stars that have the potential for habitable planets. So it's in the constellations Cygnus and Lyra. You're looking away from the nucleus of our galaxy, and I'll explain why a little later. 145,000 Mainsequence stars, largest field of view possible. And basically you monitor this continuously and you look for exosolar planets. However, things don't always go according to plan. About 2 or 3 years in, 2 of the stabilizing wheels on the Kepler spacecraft broke. And long story short, it resulted in the spacecraft being unable to continuously focus on one part of the sky. So this was Plan A, the original Kepler field. This is Plan B, a series of fields along the ecliptic plane. So it uses the sun's radiation pressure as a stabilizing force instead of the mechanical wheels on the spacecraft. And that has resulted in multiple campaigns. You make lemon out of lemonades when life hands you lemons. So instead of scrapping the project altogether when the stabilizing wheels broke in 2012 and 2013, basically you launched a secondary mission, which is K2. And the fields in yellow here represent the completed K2 missions, and the orange ones are the ones coming up. Campaign 16, which is about to begin, is going to concentrate on supernovas, which are exploding stars. I'll explain why that's significant. But long story short, it's reoriented every 80 days, and this has resulted in the Kepler spacecraft being used for far more than exoplanet discovery and characterization. In fact, summing it all up, in the world of science, it has really propelled our knowledge forward. These are all the papers that have been published in the academic arena. All the different types of papers in the world of science, astronomy, and cosmology as a result of the K2 mission. You can see that exoplanet discovery and characterization is really a small part of this. We've got anything from supernova and extragalactic discoveries, solar system science, stellar flares and stellar activity, asteroseismology, microlensing, et cetera, et cetera. It's not only used to find planets, it's also used to expand our knowledge of stars, galaxies, and the unfolding of the universe. So the key ideas for today's presentation are essentially the Kepler spacecraft has become the perfect tool for astrophysics. And an area of astrophysics known as asteroseismology has enabled us to peer into the cores of stars. For the first time in history, stars are not only skin deep, we can actually see what's going on inside of stars and gain more insight into how they behave and unfold. In the world of cosmology, the Kepler mission can be used as a better tool for calibrating type 1a supernova. They all explode at about the same brightness, so they can be used as a type of standard candle for measuring distances and ultimately the expansion rate of the universe over time. Similar to rings on a tree, supernovae are used to find out what the universe was doing at progressively different epochs in the past. And we can use that to measure the expansion rate of the universe and ultimately what this mysterious force called dark energy, which makes up about 3/4 of the universe, is, what its properties are. And finally, planetary discoveries. Third key idea of this presentation. Turns out our solar system is really weird. The most common type of planet that seems to exist in the universe doesn't exist in our solar system. Our solar system is truly alien. Now, how does this work? Kepler stares at exoplanets, and whenever a planet passes in front of a star, when you look at the light curve, there's a slight dip in the light, a very, very slight dimming. We see this in our solar system from Earth when you have transits of Venus and Mercury, which are very rare. But if you can measure this, it'd be a very, very slight dip, and then you know that there's something passing in front of the star. That phenomenon is called a transit. When a planet crosses in front of its star, as viewed by an observer in the line of, the line of sight path. Transits by terrestrial planets, a very, very slight dimming. We're talking about a star's brightness declines by 1 part in 1/10,000, 1/10,000th of a decline, or 100 parts per million, lasting for several hours. That's why you got to stare continuously at stars. We're in the silicon era now. We have CCDs, not film, charge coupled devices. So we can use silicon integrated circuits to gather the light, process the data, and analyze in exquisite detail this particular phenomenon. That's how we find planets. Now, to put this in perspective, this is the Oregon coast, one of my favorite spots in the country. And this is a very famous image. In fact, I took this picture several years ago. The Oregon coast, if you've never been there, it's very pristine. It's a very beautiful place. Highly recommend it. Right on the edge of the coast. In fact, if you watch documentaries on either the Weather Channel or the History Channel, sometimes you'll see this exact photograph. I've seen this a couple times, so it's a very famous spot. But to put the transiting of an exoplanet in front of a star in perspective, that's the Heceta Head Lighthouse right there on the coast of Oregon. I visited that lighthouse several years ago. Imagine a firefly flying in front of the lighthouse when it's fully illuminated. A star outshines a planet by several billion times. And imagine trying to detect that firefly flying around that lighthouse on the Oregon coast from Portland. And I'm talking about Portland, Maine, not Portland, Oregon. 3,000 miles away on the other side of the country. That's about what needs to happen in order to find a terrestrial-like planet orbiting a distant star. That's the monumental task ahead. That's what we're capable of doing today with the Kepler Space Telescope. So, going forward, other discoveries in addition to exoplanets have really furthered our knowledge of stars and stellar evolution. Imagine an orchestra, all right? You got bands, you got several instruments playing. And imagine a stellar symphony. It turns out that stars breathe like human beings breathe. They inhale and they exhale because stars are great big balls of incandescent gas. And it turns out that those gases rise and fall. The hot gases rise and fall. So the star slightly grows in size and slightly contracts when this process of breathing occurs. When the star inhales, it slowly grows a little bit. When it grows, the surface area gets a little bit bigger, star gets a little bit dimmer, and a tool like Kepler is able to detect that very, very slight dimming of a star. So out, it dims and cools. When it breathes in, the star contracts a little bit. When it does, it gets a little bit smaller, and it gets hotter and brighter. And those very, very slight fluctuations in brightness can be detected by Kepler. And it's also akin to this diagram right here. Sound waves traveling through different types of gases have a different frequency, like you get in a wind instrument. Or think of this. We've all gone to a party, you get a helium balloon, you inhale it, and then your voice gets really, really funny. That's because your vocal cords vibrate differently at a higher pitch when helium is in your lungs as opposed to oxygen. Same type of thing happens in stars. And it turns out that the path of the sound waves through the different layers of gas in a star can be detected now as a result of Kepler. It's an area called asteroseismology. And we can use asteroseismology, scientists can use this to measure a star's mass, a star's size, a star's age, and a star's composition in greater detail. So these are stellar acoustic waves from the Sky and Telescope January 2018 edition. You can see here the different colors, blue and red, representing acoustic waves, sound waves, resonating inside of a sun-like star. The blue and red sections moving in opposite directions. Magnify this 1,000 times, you get a pattern like this. It's like a checkerboard pattern. You can see this very, very slight fluctuations on the surface of a star as a result of acoustic waves, sound waves, literally propagating through a star. An area of physics known as asteroseismology. Now, what does this enable us to do? I got to get into a little stellar physics here, okay? This is an astronomy group. I'm showing you a diagram here of the Hertzsprung-Russell diagram. This is one of the essential tools, bread and butter, that astronomers use to understand the physics of stars. I'm going to sum it up for you as briefly as I can. Every star in the universe can be classified in terms of its properties based on its mass and its luminosity. So the luminosity of the star is right here, how bright it is. Further up you go, the brighter the star. The spectrum of the star, stars have different colors. You look up in the night sky, Orion is a great example of this. We can see Orion this time of year. The orange star, Betelgeuse, in the left shoulder, has very, very different properties than the blue star, Rigel. Red and blue mean something very, very different for a star. Turns out that the spectrum will tell us what the temperature of the star is, and ultimately what its mass and what its luminosity are. Now, on a Hertzsprung-Russell diagram, 85% of all the stars in the universe fall on this band here called the main sequence. The sun is right here. It's a yellow dwarf star, small in size compared to a lot of the stars we see in the night sky. When a star runs out of nuclear fuel, it moves off of the Hertzsprung-Russell diagram, becomes either a giant or a red supergiant. The reason they're red is because as the star expands, it cools. As it cools, the color changes. So, a main sequence star, one of the qualifications for a star to be on the main sequence is that its source of energy generation in the core is hydrogen fusing into helium. Not the entire star is doing this. Only about 10% of the mass of the star in the core is generating energy as a result of nuclear fusion. And then it transports out through the layers of the star. So when energy generation in the core balances energy that's shining away through luminosity at the surface of the star, it's called thermal equilibrium. When a star is in thermal equilibrium, it's a main sequence star if it's fusing hydrogen into helium in the core. That's why the sun can sit there and shine for 10 billion years, because the act of shining, or luminosity, is the star losing energy into outer space. Nature abhors a vacuum. So stars are hot balls of gas, and the radiation pressure of a star wants to blow the star to smithereens. But gravity balances that out, and then the energy that it loses through shining is made up by the nuclear fusion in the core. And it does that for 10 billion years for a star like our sun, which will sit there on the main sequence portion of the Hertzsprung-Russell diagram. Here, though, eventually the star is going to run out of hydrogen, and when that happens, it's going to move off of main sequence up the giant branch. Now, helium accumulates in the core of a star when this happens, and it basically doesn't do much at first. It's a little bit like building a fire and putting logs into your fireplace. As the logs burn down, the ash just kind of collects and just sits there. And if you put new logs on the fire, they're going to be on top of the old ash. That's what happens when a star runs out of nuclear fusion, or runs out of hydrogen. The helium accumulates in the core, and then the hydrogen gets shouldered out into a shell. We still have hydrogen burning here, but now the helium is dominating in the core. But it hasn't started fusing yet. So the star expands into a red giant, but it hasn't undergone fusion yet. So at that point, what's really happening on the Hertzsprung-Russell diagram is it's moving up into the giant branch stage. So this is a diagram right here. It's moving off of main sequence up the giant branch. It takes about 1 billion years for a star to do that. So this process right here represents this star right here. Eventually, the core will get hot enough and helium will start fusing into carbon. When that happens, it's called the helium flash. And again, back to our diagram, here's your helium flash. Here's the catch. During both of these processes, whether it's ascending the giant branch or it's already undergone the helium flash, they're both called red giant stars. And before the Kepler mission, we couldn't tell the difference between a red giant star that was accumulating helium in its core, and still its primary source was hydrogen burning in a shell around the helium core, versus a red giant star that had already undergone the helium flash. After the Kepler mission, we can tell the difference between those two types of stars. Stars that are ascending the branch and stars that have already undergone the helium flash. The reason is because after Kepler, we now can detect the very, very slight differences in oscillations between those two stars. Stars that have undergone the helium flash vibrate slightly differently than stars that have not undergone the helium flash. Before, again, prior to Kepler, stars are basically, we can't see inside stars. We don't know what's going on inside the core of a star. We know that the star Betelgeuse is going to go supernova at some point in time in its history. We just don't know when. It could happen tomorrow night. It could happen 100,000 years from now, because we only see what's going on outside of a star. We don't see what's actually going on inside of a star. Stars are a little bit like clouds. There's no flat surface. It looks like a cloud has a surface, but really what you're seeing when you look at a cloud is how far you can see into that cloud before the light becomes opaque and you can't penetrate anymore. So it looks like it's a solid surface, but it isn't. We know that clouds are not solid all the way through. Same thing is true with stars. The surface of a star is the point where we can't see into the star any further before the light becomes opaque, and that's called the photosphere, because that's where the photons are emitted. So on the Hertzsprung-Russell diagram, we classify stars in terms of their properties based on the properties of their photosphere. The sun is a yellow dwarf star, G2 type on the main sequence, because its surface temperature is 5,700 degrees Kelvin. But inside the core, it's 10 million degrees Kelvin, fusing hydrogen into helium. So stars, in terms of their properties, are classified based on the exterior shell, not what's going on inside. As a result of asteroseismology and the extreme sensitivity of the Kepler mission, we now can peer into the cores of stars and find out what's going on. What does this do for us? There are still a lot of unsolved mysteries in the area of cosmology and in the area of stellar evolution. And as our knowledge of stars go, galaxy formation, galaxy evolution, and the evolution of the Milky Way galaxy as a whole, it all hinges on our understanding of stars. Daniel Huber, University of Miami, or Hawaii. So as our knowledge of stellar evolution expands, so goes our knowledge of the evolution of our galaxy. Another area of asteroseismology is gaining more insight into our actual sun. So this article in Sky and Telescope goes back a couple years. It's kind of an interesting article. Could the sun superflare? What is a superflare? Turns out that Kepler is discovering that sun-like stars actually undergo superflares. Now, a flare, is when the magnetic field lines of the sun become twisted and then they blast a large chunk of plasma off of the surface of the sun. It's called a coronal mass ejection. Normally, it's not a problem, but if the Earth is lined up right in that path, similar to a shooting, a shotgun in a shooting gallery, it could overwhelm our magnetic field and be catastrophic. 1859, there was an event called the Carrington event. Auroras were seen as far south as Cuba. Now, at that time, only the telegraph existed. And even though telegraph operators were electrocuted, wasn't that big a deal compared to what would happen if we had an 1859 Carrington-level event today. It would overwhelm the power grid and destroy the entire electrical grid. The backbone of our electrical grid is about 300 high-voltage transformers. It takes about 6 to 8 months to manufacture one of them. Now, if one goes down, it's not a big deal, but if all 300 go down at one time, we're talking about the potential to have no electricity for several months, maybe even years. No electricity means no power, no internet, no air conditioning, no heating. It also means you can't pump gas, you can't transport. It means food can't get to your grocery store. It basically means the breakdown of civilization. The National Academy of Sciences did a study on this, and if we had a Carrington-level event today, it's estimated that as much as 1/2 of the population of the world could be wiped out. It could be catastrophic. Well, this is nothing compared to a superflare, which could be 10,000 times stronger than the worst flares that the sun has ever put out. So the question is, could our sun undergo a superflare? As a star ages, it rotates more slowly. So the probability of a superflare goes down, supposedly, with time. However, what Kepler discovered was that older stars actually spin faster than we had originally thought that they would. So that raises some serious concerns about the possibility of a superflare. However, long story short, it's not likely to happen because the article was released recently that talks about the relationship between stellar activity, age, rotation rate. It actually breaks down as a star gets past its midlife point. So a solar superflare, not likely, even though we're seeing superflare activity on sun-like stars in other parts of the universe. All right, supernovas. Turns out that Kepler has enabled us to more completely map the light curve of a supernova. These are two type 2 core collapse supernovas. A type 1a is when a white dwarf in a binary system gravitationally sucks matter off of a giant companion star, and as that matter accretes, eventually it gets to the point where it's unstable and it'll blow up. Type 1as are the holy grail in astronomy because they're great standard candles. A 100-watt light bulb is a 100-watt light bulb, whether you're looking at it up close or far away. If you know how intrinsically bright an object is, you can measure how far away it is, and then you can measure the expansion rate of the universe. However, what we don't know is whether type 1as are as a result of colliding white dwarfs or a white dwarf that accretes matter from a giant star. There can be two different types of 1as. The Kepler mission gives us a more complete data set from its light curve. And it turns out that if it's two colliding white dwarfs, there will be no quote-unquote slight bump in its light curve. Whereas if you have a white dwarf that accretes matter from a red giant, as the star explodes, it'll ram into the red giant star, and there will be a slight bump in the light curve. So you can tell the difference between the two. So that helps us to better calibrate 1A supernovas as standard candles. Another discovery as a result of the K2 mission. Now, let's get into planets as we wrap this presentation up. Before Kepler, most of the planets, the exosolar planets that were discovered, were the so-called hot Jupiter types. One of my favorites is WASP-12b. A hot Jupiter is basically a Jupiter-sized planet that orbits really, really close to its star. WASP-12b is a classic example of this. It's basically a Jupiter-sized planet that orbits even closer to its star than Mercury. So the gravity is literally distorting, warping the shape of the planet and causing it, it's causing it to shed a lot of material in 1 year. What I like about this particular planet is it has an overabundance of an element called corundium in its atmosphere. And corundium is the substance on Earth that makes rubies and sapphires. Now, it's one of the hardest substances on Earth. But on a planet like WASP-12b, it vaporizes in its atmosphere and it rains out. So it's not inconceivable that you could literally have molten sapphire rain in the atmosphere of a world like WASP-12b. It's really, really strange. Some of these hot Jupiter planets are really weird. But these are rare planets. Getting into the composition of planets in our solar system, we can basically break it down into three types. They're the so-called terrestrial or rocky Earth-like planets. So Earth is made of mostly rock and then just a little bit of ices. Jupiter and Saturn are fundamentally different. They're gas giant planets. So they're made of mainly hydrogen. They're made of mainly hydrogen and helium and then trace amounts of ices and very, very small amounts of rocks. And then you have what's called the ice giants. That's Uranus and Neptune. So compositionally, these are very, very different types of planets. It turns out that with Kepler, we can measure or determine what types of planets we're discovering based on their density. And you get the density by measuring the radius and the mass. And here you can see a plot of the different types of just a handful of some of the planets that Kepler has detected. The blue line here is ice. If you're above the blue line, then that means that you are actually less dense than ice, the planet is, which means it has a higher likelihood of having a thick gaseous envelope and being not Earth-like at all, more like Neptune, so to speak. And then, of course, the yellow line is terrestrial rocky, and then the green line is iron. So if you're below iron, you're likely not an Earth-like planet either because you're just too dense. So here's the punchline. Since Kepler was launched in 2009, it turns out that there was an explosion. Over 70% of the exoplanets discovered in the universe so far are a result of the Kepler mission. But if you map out our solar system in terms of size and composition, planet types, Mercury, Mars, Venus, Earth here, Neptune and Uranus, the ice giants here, notice the types of planets that are being discovered as a result of the Kepler mission. Most of them fall in between Earth and Neptune. So they're either a mini Neptune or a super Earth type. That's the most common type of planet in the universe that's being discovered. What are super Earths? Again, the definitions are a little bit fuzzy, but somewhere between 1.2 and 2.5 Earth radii and 5 to 10 times more massive than the Earth. That's classified as a super Earth. A mini Neptune is less than 3 Earth radii. To date, Kepler has discovered 700 super Earths and 900 mini Neptune type planets. The majority of the planets, 1 out of every 3 planetary systems discovered, either has a super Earth or a mini Neptune, as opposed to 1 out of every 200 that's a hot Jupiter-like, which you saw with WASP-12b. So why is that? What exactly is going on? Is it a clue to how planets form and how they move in a planetary system? And it's the possibility that maybe super Earths are really mini Neptunes with their atmospheres blown off. They form on the outskirts of our solar system, gravitationally migrate in, not our solar system, but a star system. And as they migrate in, the radiation pressure from the star blows off the atmosphere, and you're left with a rocky core left over. That's more of a mini Earth. I'm sorry, a super Earth. So, and that's the Sky and Telescope article talks about this. A lot of the planets that are being discovered that are so-called super Earths have a period of 4 days or less, which means they're really, really close to their stars. Our planet takes 365 days to go around its sun. These planets are just whipping around their stars really, really fast. So how do they get that close? So there's some theories about where is the solar system's super Earth? Why are we so weird, and why are we so different if the most common type of planet in the universe is either a super Earth or a mini Neptune? Well, one scenario could be what's called the grand tact scenario. Jupiter is kind of the gravitational bully of our solar system. Now, Jupiter gives and it takes away, right? Life on Earth wouldn't be possible without Jupiter. 1994, Shoemaker-Levy 9, better Jupiter than us, because if it hit us, we'd be in real trouble. So Jupiter, the gravity of Jupiter sucks these comets in and either flings them out of the solar system or swallows them up. You need a good Jupiter to have life. However, early in the solar system's history, when things were kind of just getting going, it was a more chaotic and random place. It's believed that Jupiter migrated into the inner solar system and then gravitationally may have flung out any planets that existed at that time that were either super Earths or mini Neptunes and then migrated back out again. Now, it's highly speculative. There's no data to support this, but it's one theory. And of course, another theory is the Planet 9 theory. There's evidence to suggest now that there's a ninth yet-to-be-discovered planet on the outskirts of the solar system, 3 times further away than Neptune, that may have the properties of either a super Earth or a mini Neptune. And of course, there is a serious attempt to find this planet by all people, Mike Brown, the guy who killed Pluto. So he's trying to make up for it by finding the solar system's super Earth to make us look more normal, and hopefully we fit in with all the other star systems out there that are being discovered. So to quote it, John Armstrong, Weber University, if it turns out that we do have one, talking about the possibility of a super Earth existing in our solar system, if it turns out that we do have one, that would make me feel better, because it would mean that we're more normal. I'm concerned about us being normal, because if we're not normal and there's something really special about the solar system, then life is probably rare. But if we're just a garden variety solar system, then it gives me hope that life is not rare. So what it comes down to is we are weird, because there's this gap between Earth and Neptune, and that gap turns out to be where most of the planet types are found as a result of the Kepler mission. So I'll finish with this. What is habitable? Again, star, the green zone is the habitable zone. That's where you find the highest likelihood for water, stable water on a planet. If you were to move in just a little bit, about 0.95, 1 astronomical unit is the distance from the Earth to the Sun. 95% of that, you're getting pretty close to being too warm and a runaway greenhouse effect taking over and a planet becoming more like Venus. You go out to about 1.5 astronomical units, it's too cold. Oceans freeze, snow falls, light radiates away, you get a runaway effect, you get snowball Earth. So, a lot of the Kepler worlds that fall in between Earth and Neptune, they were mapped out to see where exactly they fall in the potential habitable zone. The details of this chart are on this website here. I'll try to simplify this. Basically, anything in green, light or dark, are what we call optimistic habitable zones. Earth is right here. Now, this is the energy that a planet receives from its star versus the temperature. Our sun is about 5,700 degrees Kelvin. Move over, Earth is right there. Now, if you go this way, you're getting to where Venus is, too hot, but right on the edge is early Venus, what Venus may have been like 1 billion years ago. Our sun as a main sequence star is gradually getting brighter with age. As it gets brighter, it gets hotter. So, but in the past, Venus, when the star was dimmer, may have been more Earth-like. So it may, planets, Kepler worlds that are being discovered fall in this region, optimistic habitable zone, possibility for the conditions to exist for life. Go the other way, Mars. Again, early Mars received a lot less energy from the sun, but it was believed that Mars was more Earth-like in its past too, as a result of a magnetic field and a thick atmosphere. So, a lot of these worlds are being mapped out. Now these, the darker green is more conservative habitable zone based on climate conditions on Earth. So, long story short, this is not an exact science. There's still some disagreement, there's still some fuzzy boundaries, there's still some speculation that's involved. But NASA and other agencies who are discovering these Kepler worlds are undergoing attempts, if you will, to really place them in the zones for the possibility of life to exist. So that's essentially what's meant by this graph right here. And again, the super Earth types, and then the mini Neptune types based on their size and mass. So summing it all up, Kepler has become a tool that's used for far more than just exoplanet discovery. Here's how it breaks down. Astrophysics discoveries, exoplanet discoveries. In terms of exoplanets, number of stars observed during the primary mission, over 150,000. Number of confirmed planets that were discovered as a result of Kepler, over 2,400. Number of planets with potentially habitable worlds found by Kepler, 29. Planets that orbit solar mass, sun, stars like our sun, Kepler has confirmed 964. And then planets that take longer than 365 days to orbit their whole stars, meaning they're far enough away to be in that habitable zone, 28. Look what's happening on the astrophysics side, though. 43,000 galaxies observed, 21 supernova. The next campaign is going to study supernova. That's campaign 16 coming up. Star clusters, Uranus and Neptune were studied in more detail in our solar system. 3 dwarf planets, 6 solar system moons, including Titan and Enceladus, 2 of the most interesting moons in our solar system. Comets, trans-Neptunian objects, and asteroids. So, Kepler has become a very versatile tool for expanding our knowledge, not only of planets, but more importantly, stars, galaxies, astrophysics, all the different topics of astronomy that are of interest to us, to help us understand and answer some of the more mysterious questions about our solar system, about our galaxy, its evolution, its history, and its unfolding. And that's my talk. Thank you.